200 years ago, a farmer could keep meat fresh through an entire summer with no electricity, no chemicals, and no power grid. He did it with a hole in the ground, some straw, and a frozen lake. Today, we spend billions on refrigerators that break down in 5 years. Back then, families built something that worked for generations, and almost nobody remembers how. Stick around because we're about to walk through the exact method step by step, and one piece of it still works today, sitting in your own backyard. Picture a farmhouse kitchen in 1850. No buzzing compressor, no hum of electricity, just a quiet cellar packed with something most of us never think twice about: ice. It sounds almost too simple, but keeping food cold without power was once the difference between a family eating through winter heat or starving by February. Meat spoiled in days, milk turned sour overnight. So people did something we've completely forgotten how to do. They learned to store winter itself. Every January, families and entire communities would cut massive blocks of ice from frozen ponds and lakes. They weren't doing it for a treat. This was survival. This ice would need to last them through July, August, sometimes even September. And this wasn't some small backyard habit. At its peak, the U.S. ice trade employed an estimated 90,000 people and was capitalized at $28 million, using ice houses capable of storing up to 250,000 tons each. That's not folklore. That's an entire industry built on a frozen pond. Here's the part that surprises most people. An unprotected block of ice in summer heat can vanish within days. No structure, no insulation, just gone. And yet families using nothing but wood, straw, and dirt kept ice solid for 6, 7, even 8 months. Think about what that meant for daily life. Fresh milk in July, meat that didn't have to be salted into leather just to survive the heat. This wasn't luxury. This was the original cold chain and built entirely from materials sitting in a person's own backyard. And the method behind it wasn't guesswork. It was a quiet science refined over decades, passed down through families who understood something most of us never learned. Cold isn't something you create, it's something you trap. That idea right there is the heart of everything we're about to cover. Hit subscribe now because the next part is where this gets really useful. Here's where most people go wrong when they imagine this whole system. They picture a giant block of ice just sitting in a shed, slowly melting away like an ice cube on a countertop. That's not even close to what was actually happening. The real secret wasn't the ice at all. It was the air around it. Ice doesn't melt because of heat touching it directly. It melts because warm air constantly moves around it, transferring energy into the surface. Stop the air movement and you slow the melting dramatically. This single principle is the entire foundation of ice house design. So instead of just stacking ice in a box, builders created something closer to a thermal fortress. Thick walls, minimal airflow, and most importantly, layers, ice packed tightly with insulating material between every single layer. That insulating material is where things get interesting: sawdust, straw, wood shavings, even dried leaves in some regions. These materials seem almost too humble to matter, but they trap tiny pockets of air, and trapped air barely moves. Without air movement, heat transfer slows to a crawl. This is the exact same principle modern refrigerators use today, just executed with completely different materials. Your fridge uses sealed insulation and a compressor cycle. Your great-great-grandparents used a hole in the ground and a pile of sawdust. Different tools, same underlying physics. Most people assume our ancestors were just making do with primitive tools. Actually, they understood something most modern homeowners never think about. Insulation matters more than the cold source itself. You can have all the ice in the world. Without the right barrier around it, it's gone within days. That single shift in thinking, protect the cold instead of just creating it, is exactly what made the entire system work. And it's also the part most people skip when they try to recreate cold storage at home today. So how did an actual ice house come together? Let's walk through it. Step 1 started in winter, often January or February, when ice on ponds and lakes reached its thickest point. Workers would cut large blocks, sometimes 2 feet thick, using saws and specialized ice plows. Step 2 was transport, and timing mattered enormously here. The faster the ice moved from the lake to storage, the less was lost to early melting. Sleds, wagons, sometimes simple human muscle, hauling block after block before the spring thaw could touch them. Step 3 is where the real engineering appears. The ice house itself was rarely just a shed above ground. Many were built partially underground, taking advantage of the earth's natural insulation. Walls were thick, sometimes double-walled with an air gap, similar to how a modern thermos keeps coffee hot for hours. Inside, ice wasn't simply piled up. Builders layered it carefully. A base of insulating material at the bottom, then ice, then more insulating material packed tightly around every block. This continued layer after layer until the structure was full. Drainage mattered just as much. As ice slowly melted, that water needed somewhere to go, or it would pool and accelerate the melt. Here's proof that quality of build mattered more than luck. Operations running well-insulated ice houses and barges kept their seasonal losses to about 20% of the annual harvest, while most companies saw nearly 50% of their ice melt away to nothing. Same ice, same climate. The only difference was how well the structure was built. This wasn't isolated to small farms either. Companies shipped ice from frozen lakes in the northern states all the way to the Caribbean, packed in sawdust inside the holds of ships, and it survived the entire journey. If sawdust could keep ice frozen on a boat crossing tropical waters, imagine what that same principle can do in your backyard right now. You don't need to dig a cellar or harvest a frozen lake to benefit from this knowledge. The underlying principle scales down beautifully for modern use, and you can test it this weekend with materials you probably already own. If you want to try a small-scale version, start with an insulated container. An old chest freezer shell with the motor removed works well. A large wooden crate lined with thick cardboard works too. Even a sturdy plastic storage bin can do the job if it's deep enough. Line the bottom with a thick layer of sawdust, straw, or wood shavings, at least 3 to 4 inches deep. Next, place your ice blocks or frozen jugs of water on top of that base layer. Frozen gallon jugs work especially well here since they melt slower than loose ice and won't leave you with a slushy mess to clean up later. Pack more insulating material tightly around the sides, leaving no exposed surface touching open air. The goal is total separation between the ice and the warm air outside, the same separation that kept entire farmhouses stocked through July. This same insulation principle isn't limited to ice. The same cool, sealed-off space that protects a block of ice can just as easily protect root vegetables, dairy, or anything else that spoils in heat. Potatoes, onions, and hard cheeses all benefit from sitting somewhere dark, insulated, and untouched by warm air. The physics doesn't change just because the contents do. Seal the top loosely enough to allow minimal airflow, but tightly enough to keep warm air from rushing in. A loose-fitting wooden lid or a thick folded blanket works better here than a tightly sealed plastic lid, which can trap moisture and encourage mold over time. Every time that lid opens, you're letting heat in and speeding up the melt, so minimize how often you check on it. Treat it like a treasure chest, not a snack drawer. One common mistake people make is using too little insulating material around the edges. Even a thin gap of exposed ice touching open air dramatically speeds up melting. Pack it generously, especially around corners and seams where air tends to sneak in unnoticed. Another mistake is skipping drainage planning entirely. Even small setups need somewhere for melted water to go, or you'll end up with a soggy mess that speeds up heat transfer instead of slowing it. A few small drilled holes near the bottom, draining into a tray underneath, solves this easily. For best results, location matters just as much as construction. Place your setup in shade, ideally against a north-facing wall or underground if possible, where ambient temperature stays naturally lower throughout the day. Even moving it a few feet out of direct afternoon sun makes a noticeable difference. Realistically, a well-built small-scale version using these old methods can keep ice solid for weeks rather than days, even through summer heat. That's a dramatic improvement over a basic cooler, and it costs almost nothing beyond materials you likely already have lying around your property. This isn't about replacing your refrigerator, it's about understanding a backup system that worked for generations before power grids existed and still works quietly today for anyone willing to try it. Once you build one and watch it hold ice through a heat wave, this stops feeling like history, it starts feeling like a skill. Let's talk numbers, because this is where the comparison gets genuinely interesting. A modern refrigerator costs anywhere from a few hundred to several $1,000s up front. Add electricity costs running continuously every single day for years. Add repair bills when compressors fail, which they eventually do. Now compare that to sawdust, straw, and ice you can either harvest yourself or buy cheaply in bulk. The upfront cost is a fraction of a refrigerator. The ongoing cost, especially if you have access to a natural water source that freezes in winter, can be close to nothing. Obviously, nobody's suggesting you abandon your refrigerator entirely. Modern convenience exists for good reason. But during a power outage, an emergency, or for off-grid living, this forgotten method becomes far more than a history lesson. It becomes a genuine backup plan that doesn't depend on the power grid staying online. There's also a quieter benefit worth mentioning. No electricity means no humming compressor, no electric bill ticking upward, no dependence on a system that fails the moment a storm knocks out power for a week. For homesteaders, off-grid families, or anyone preparing for emergencies, this old knowledge solves a problem modern refrigeration genuinely struggles with. The bonus tip here is simple. Even just one insulated, sawdust-packed cooler kept in a shaded spot can serve as emergency backup storage during outages. You don't need a full ice house to benefit from the core principle. You just need to understand it. So here's what to remember. Cold isn't something you generate, it's something you protect. Insulation matters more than the ice itself. And materials sitting in your own yard right now could recreate a system that fed entire families for generations, long before electricity ever entered the picture. Here's something worth sitting with. That root cellar your grandparents had wasn't outdated technology. It was a different kind of smart, one built on patience and materials instead of plugs and power bills. We didn't outgrow these methods. We just forgot we ever needed them. Forgotten knowledge like this rarely stays useful by accident. It stays useful because the physics never changed. Only our memory of it did. And the families who understood that lived through hard winters, long power outages, and lean years that would break most modern households. If this kind of practical old world know-how is something you want more of, subscribe and stick around for the next one. We're heading into root cellars next, the forgotten system that kept vegetables fresh through an entire winter without a single refrigerator involved. Stay curious, stay capable. We'll see you there.